first. Oh, perfect, I think. Hold on. I just need to see how this is like. So configuring things. Oh no, it's flipped. How do I... If I do this. Huh? Oh. 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 Oh, wait a second. What if I tutor like this instead? Oh, that could work. Maybe. Question mark. I can write like this if the camera doesn't want to cooperate. Okay, how loud is the mic? I think it's pretty good. Ah, that's great. I also have this awesome Andy Bear that you can see. More about him later. I like, wait, this is actually pretty decent, I can't lie. It's going better than I thought it would be going. I do have a delay, so hold on, just set up first. Okay. Let me just get some water to feel my voice, because my voice is not at its peak condition. And I need to start projecting my voice a bit, so then I can get. Look, I have no idea if when this VOD comes out you're gonna see all of this, but you know what, it's fine. Okay, just copy this real quick. Let me just, oh boy. Sorry, this is taking a while. Okay, hello, people. Hold on, this is taking a bit. Let me just do it one more here. Where is it? Here we go. Okay, so this is kind of my first time streaming on YouTube, especially like this, so I don't know what to expect. Just expect some disturbances and stuff. So I'll just give it a minute to let everyone see it. So yeah. And this will be saved as a video anyway, so don't feel pressured to join the stream. If you want to leave, you can leave by all means. do what else you want to do. But I will be here teaching anyway because streaming is gonna be easier than having to make a video and then editing that all the time, you know? It's not the ideal way to do things. Okay, give me a moment. I just need to blow my nose. Okay. Let me just monitor everything and we should start. Okay, let's do this. Okay, wait, that was a lie. Let me just open up my notes and stuff. Okay. Hello everyone, and welcome to General Chemistry with Antimatter. So today, I will be discussing general chemistry with you guys, specifically hydrocarbons. I'll be teaching you the basics and as well as some other topics regarding hydrocarbons. Now, before we get started, this video is thankfully sponsored by Bandy Bears. I'm pretty sure most of you know about this, but we'll get onto it later. Let's start with our first topic. Now, our first topic will be chemical bonding. Before we get into what hydrocarbons really are, let's get a basis first of chemical bonding. Now, I'm sure most of you are familiar with what chemical bonding is. You've probably heard the term multiple times, but maybe you don't know the exact meaning of it. So I'll be here to tell you what it is. Excuse me for the poor angle and the poor handwriting. We're gonna have to deal with it now because my camera is a little wonky. Yes, this is science. This is general chemistry. Specifically at a grade 12 level, but I will try my best to make this applicable to all. So, chemical bonding. This is a process that a lot of elements go through. Now, chemical bonding basically just means that there are processes that bond specific elements together. Now, chemical bonds, in particular, the term chemical bonds, pardon the handwriting again, chemical bonds specifically refer to the forces. So this will refer to the forces that are holding them together. So it'd be the forces holding these atoms, these elements together, while chemical bonding is the process. So that's how you differentiate them. Now, when it comes to chemical bonding, there are three main types. So these three types would be ionic bonding. We will also have our second type being covalent bonding. And our third type being excuse me, metallic bonding. So these are the three main types of chemical bonding. Now, mainly for the lesson that I have been, or mainly for today's stream, we'll be talking about ionic bonding. Alright, yeah, sure. If you're grade 9, this will still help. Because maybe at some point you'll probably have to learn this. But anyway, let's start with ionic bonding, since this is the one that I'm mostly knowledgeable about because this is what was mainly taught. Okay, so these bondings, these ionic bondings, wait, I don't have an eraser. Sorry. I'm gonna have to deal with tissue for now. So, ionic bonding. What exactly is ionic bonding? Now, it is basically the bonding of ions. Now, ions are basically elements that have a specific charge, negative or positive. They're charged ions. So, so ionic bonding is formed by the attraction between oppositely charged ions. Basically, if you were to have one ion that is positive, that is also interacting with an ion that is negative. Now, these positive ions and negative ions have a term or a nickname. So the positive ion is called cation. Sorry, let me tilt the whiteboard because it's a bit hard to see. I also write bigger. So the positive ions are called the cations, and negative ions are called anions. So that's how you can differentiate them. If it's a positive, it's a cation. If it's a negative, it's an anion. Now, these ionic bonds are formed between metals and nonmetals. So these are basically just groups within the periodic table. If you're familiar with it, it should look like this, if I'm not mistaken. Should be something like this, yeah. So in the periodic table, there are metals and nonmetals found throughout. So these ionic bondings are exclusive to only metals and nonmetals. Now the cations are the metals in this case, and the anions are the non-metals. So another way you can think about it is if you're given a problem and it's talking about a positively charged ion, you already know that it is a cation, and you also know that it is a metal. But if the ion is negatively charged, you know that it is an anion. And if it's an anion, it is also a non-metal. Very simple. Honestly, I have no idea if I'm pronouncing it right, but unfortunately, we're gonna have to deal with that. So, an ionic bond can also be the if I were to graph it like so, let me just erase this again. I don't have a whiteboard, my apologies. So an ionic bond also includes the transferring of electrons. For example, let's say we have an atom here, and it has an orbit, and it has an electron right here. Right here is an electron. And then we have another atom right here, is atom number 2, and has another orbit as well. And let's say he has multiple electrons. Let's say this second atom has a lot of electrons. Now, atom 1 over here and atom 2. If you notice, all it takes is for this electron to go to this spot for B to have basically a perfect looking side. He'd have 2 electrons at the top, 2 electrons at the right, 2 electrons at the bottom, and if atom 1 were to give his electron, it would be 2 electrons on the left, perfectly equal. Now when atom A, or atom 1, transfers the electron, it then becomes an ionic molecule. So the atom 2 over here will end up having the electrons that atom A gave him, making him have this. So that's what an ionic bond is. It also includes the transferring of electrons, which is why we're talking about it. Sorry, what do you mean, what does it called again? B equals 1, yes. Well, in this case, B just means it's a numbering. It's a numbering system. It doesn't necessarily mean that it's boron. It's just to differentiate it. So that A is different, B is different. It's just a fancy way of saying they're different. It could be boron, maybe, but in this illustration, not quite. Okay, so that is what an ionic bond is, more or less. Now, when nonmetals react with metals, cations and anions, they gain or lose one or more electrons. Now, the metals give out their electrons, so they stick together in an ionic compound. So, we're going to have a easier visualization of this. So, I'm going to draw my best the periodic table. The upper part, we're not going to count the ones at the bottom. The lanthides, I believe that's what you call it. Okay, so it looks something like this. Now, there are elements inside each of these boxes, right? Now, the elements on the very right here, these elements, I believe it's helium, and then yada yada. All of these elements in this side, specifically this side, are stable. They're perfectly stable. So, all the elements in these sides, all of these, when they make compounds, when they have ionic compounds, they want to be as stable as this. They want to achieve complete stability, just like this row, which in this case is the 8th, or rather the 8th column. So, when we're dealing with ionic compounds, the reason why one atom gives its electron to the other atom, or loses its electron and gives it to the other one, is for the sole purpose for them to remain stable. Okay. Yes, exactly. Okay. Again, slow erasing because I left my eraser. Okay. So, let's have some cases. Specifically, we're going to start naming ionic compounds. So, again, pardon the camera because for some reason it doesn't want to flip. But okay, so let's say we have this case. A very simple, easy case. We're going to have magnesium plus 2 plus oxygen minus 2. Okay. You might be looking at this and might be a little confused. However, in my previous video, I mentioned what these things are. But if you don't, then it's fine. I'll have a bit of a reviewer. Now, again, the periodic table of elements. Now, there should be 8 rows, or 7 rows, disregarding this, right? So you're going to have some here, some here. You're going to disregard this part. You're going to disregard this block. You're not going to count this. We're only going to count this and this. Now, when it comes to the charges of these metals and nonmetals, the first 3 elements from these, the first 3 columns, so there'd be 1 column here, 2 column, the second column, and then the third one. So any element within this range, within these rows, will have a positive charge. So this will have a positive charge of 1, positive charge of 2, and a positive charge of 3. Anything beyond that point will have a negative charge. So this will have negative 4, followed by negative 3, followed by negative 2, and then there should be a negative 1, but because of how poorly I drew this, you won't be able to see it. But there's supposed to be 5 rows here. There you go. 5 rows, and then the stable row. So again, 2 rows on the left, 5 rows in this one, and then the 8th row is all stable. So if we're going to look for magnesium, where would we find it? Magnesium, if I'm not mistaken, is found in the 2nd row, which is why it has a positive 2 charge. Oxygen, on the other hand, is found on the 6th row, which has a negative 2 charge. So we can then just use what we learned and just put the charge here. This is their ionic charge. This is the charge of their electrons. Why is it positive 2 and why is it negative 2? Now the reason why it's positive 2 and negative 2 is because we're comparing it to this. Oxygen is 2 electrons subtracted to being stable, while magnesium is an additional 2 electrons or additional 2 charges from being stable. If it's on the left, it's addition. If it's far on the left, rather, in this block, it's addition. If it's right beside this row, it's subtraction. But enough dilly-dallying with this part. Let's get into the equation. So again, we have this here. Magnesium, or a magnesium ion, plus an oxygen ion with these charges will equal into what? Now, simply, the answer will be magnesium oxide. But how did we get into magnesium oxide? Do you really just combine the letters, combine the elements, and just write it as is? In a sense, yes. But I'll show you the exact process. So I'll erase this, and I'll just refer back to it later. But it's good that we have a basis as to why they have these specific charges. So, how did magnesium plus oxygen equal magnesium oxide? Or specifically their ions? Well, there is a process that my teacher has coined as coined as the crisscross method. It's very simple. Yes, basically that. Yes, 2 positively charged particles plus an oxygen atom or ion with 2 negatively charged particles. So it's quite simple, again. So you're just going to get the charges of these, you're going to disregard the sign, and you're just going to distribute it to their subscript. So it would be rewritten as so, magnesium with a subscript, subscript, and then this. However, I was told that if their charges have the same numerical value, basically if they're both 2, if they're both 1, if they're both 3, you can just cancel it out, or maybe divide it by 2 as well, since they're both divisible by 2, and it'll just be magnesium oxide with no subscript, nothing. Very simple. This is your first case. This is just combining, specifically, let me list here, case 1. So that's case 1. Case 1. So that's going to be simple metals, which can be found in groups 1 to 3, and the combination of simple nonmetals. Which is the remaining groups, group 4 to group 7. So that's what case 1 is. That's what we just did. Magnesium and oxygen. Okay. Okay, so next, we have another one from this example that I was given. So again, with the naming of ionic compounds, we'll have the same case, being simple metals and simple nonmetals. But this time, instead of having equal charges, we can try it with these 2 others. So I have this positive charge of 2 plus nitrogen with 3 negatively charged particles. Now this is supposed to result into 3 and nitrogen 2. Oh shoot, 2. Now if we're gonna apply the same method that was taught earlier, we are just gonna be distributing the amount of particles found in the other element and distributing it to the subscript, like so. Which is why we'd be given this. Ca with a subscript of 3 and nitrogen with a subscript of 2. Unfortunately, I cannot talk about these formulas because the reason I'm making this is as a reviewer for my school. Once I am done with this, I could research about more on chemistry because, to be honest with you, my knowledge in chemistry is not that good. I could research about it more and more once I have more time, and I could tutor chemistry, science in general, biology, physics, astronomy, geology. I could also branch into mathematics, calculus, differentiation, integration, algebra, advanced algebra, etc. You get the point. The main reason this channel exists is actually to serve as a school reviewer for my school. So, unfortunately for now, I cannot dive into other topics. Do you also... I could try explaining different types of volcanoes. We have a shield volcano, I believe, cone. Oh my goodness, that's a throwback, but I cannot get off topic for now. So that's what case 1 is. Let's go back to this first, and I will entertain these comments in a bit. Yes, there is a bunch of lava. I don't want to be the nerd, but I believe it's called magma if it's still under the crust. Okay, anyways, let's go with our second case. Let's go with case 2. Okay, now for case 2, instead of it being simply simple metals and non-metals, we're still gonna have the simple metals. Let's like so. But we're also gonna have polyatomic ions. So what is a polyatomic ion? Well, just judging from the prefix poly, that just means more than one. So that means these ions have more than one atomic composition. Is it called... Oh, wow. Okay. So this is what case 2 will be talking about. Again, we are in the context of naming. So we are only doing the equations to find out the result, and then using said result to get the name. But it's also helpful that we have the whole result. Now, there's a lot of polyatomic ions that I recommend you search if you really need it. There's, I believe, more than 20. Just to name a few, there's nitrate, there's nitrite, there's hydroxide, cyanide, chloride, chlorate, hypochlorite, periodate, iodate, iodide, yada yada. There's a lot. But we're gonna talk about the more common ones, like nitrate, nitrite, sulfite, chromate, chromate, and dichromate, the more common ones. Okay, so let's start with our first problem. Okay, I will do this part even though we've already talked about it. Just to differentiate, this is an ionic equation, meaning that it'll only affect the charge rather than it being a chemical equation. Because in the chemical equation, the results can vary, it is possible, but for the ionic equation, this is what our basis will be. So again, we're going to have magnesium with 2 positively charged particles, and then we're going to have a sulfate ion, which has a constant positioning like this. 1 sulfur, 4 oxygens, and then it has 2 negatively charged particles. Now, again, using the method earlier, these 2 would cancel out because they have the same numerical value, and this would just turn into literally the combination of them. Magnesium sulfate. Now, excuse me, I'm a bit under the weather. So instead of it just being magnesium ion plus a sulfate ion, you just combine it literally. So this will literally be read as magnesium sulfate, just like that. Now the ending can change depending on how many, depending on the charge, or rather depending on the subscript, sorry. If there's 3 oxygens, it would be sulfite. Same thing goes for nitrate, nitrite. The lesser the subscript, it will end in an ite, but the more there is, it would end in an ate. Okay, your topic right now is about volcanoes. Interesting. I'll try to see what I can do with that. To be fair, my main way of teaching is I just research for a bit, and then once I understand it, I'll just go straight on the whiteboard and see what I can do. But again, I have to stick into chemistry for the sake of this being a part of my school. But I will let you know if I could upload about other topics as well that you might want. Just feel free to message, comment, whatnot. I'll try my best to help. Okay, next. So this is a very simple case. Again, since they have the same charges. Okay, let's go to the next case. That being ones with different charges. Aluminum that has three positive particles, and then carbonate or carbonate. Okay, so since there are different charges, we can't just cancel them out. Instead, we're going to give it like this. So aluminum will then have a subscript of 2, while our carbonate, in this case, we're going to have to put it in a parenthesis to emphasize that this is carbonate, and then we're going to give it a subscript of 3. Just like that. We're still doing the crisscross method, but we're keeping this untouched. Just like that. So this is literally going to be your answer, which will be read as aluminum carbonate. Aluminum carbonate. Very simple, right? Quite easy to understand. Okay, so I will have to speed this up because we still have a lot of topics, and I plan on getting at least halfway before I have to sleep. So let's move on to case 3. So for case 3, we have the combinations of transition metals and simple nonmetals. So transition metals are found within the D block. Now what is the D block? So again, if I were to draw you a periodic table of elements, like this, there you go. The periodic table of elements, this is the D block. This giant, short, wide section of the periodic table of elements is considered the D block. So a transition metal will be basically any of the cations here with 2 or more charges that are found within the D block. So that's what a transition metal is. And then the combination of simple nonmetals. So that's what case 3 is about. So let's dive into 1. Oh wait, before I do that, again, some of these have default names, such as, like for example, if we're to have iron as the example, again, if it has 2 or more charges, so you can rewrite it like this, iron, and instead of writing the positive charge or whatnot, in word format, it'll just have Roman numerals, like so. Maybe you've come across this already or not. But this case, iron 2, you can read it as ferrous in the context of ionic bonds. So if you're going to combine it with other ions, you're going to refer to it as ferrous, or ferric if this is 3. This is 3. Ferric, like so. So let's have an example. Again, I recommend you search up your transition metals because there is also a good amount of them, just like the polyatomic ions. So we'll just do one example with the method because again, it's pretty simple. I guess the only thing I'll add here is the naming for this because it can get a bit confusing. So I won't show you the process anymore. So it's just copper with 1 positive charged particle, and then oxygen with 2 negatively charged particles, or oxide rather. This will turn into Cu2, and then O, which is read as copper 1, or it could also be called cuprous. Cuprous oxide. So it could be read as such. So if it's 1 charge, it's cuprous, but if it's 2 charges, it's cupric in this case. Okay, so that's how you name for case 3 with the transition metals. So just a refresher, case 1, it's almost as simple as that, simple metals and nonmetals. Simple metals and simple nonmetals, that'll be just magnesium oxide, it'll just be straightforward. For case 2, we have polyatomic ions, so those are the ones that have sulfate. And for case 3, transition metals, these will have cupras, this will have cupric, this will have the ic and the us. Now, for our last case, which is case 4, we will have, oh wait, there's a lot of examples. So we're going to have transition metals and polyatomic ions, like so. Polyatomic ions. So we're just going to combine both concepts into one. So let's say we have this. I won't show you the process because it's pretty simple already. +2 plus sulfate. Again, just crisscross these. You're going to be given this. Cancels out those since they have the same numerical value. So this will be read as cupric the previous example with the copper was supposed to be cupras, but anyways. So this one's cupric. So this is cupric and then sulfate. It's very straightforward. You just combine the words. Just know the difference between Rick and us, and then 8 and ite. Just know your polyatomic ions and transition metals. So these are what covalent bonds are. Again, atoms that are sharing electrons in order to achieve stability. That's what an ionic bond is. An ionic bond is in its most basic form. Now for covalent bonding, which you won't really talk too much about, covalent bonding is formed between nonmetals. So how this works is, again, electrons being shared. However, it is between two nonmetal atoms. So in a diagram, it would kind of look like this. You'll have 2 here and another circle right here. Now I know it looks like a very inappropriate drawing, but this is how it looks like so. Now, some facts or things you should note about covalent bonding is that they have very low melting and boiling points. They do not conduct electricity, and they also don't dissolve in water, for whatever reason. Now, for naming these covalent bonds, there are rules. There are rules for covalent compounds, rather. Covalent compounds. So the first rule is naming the first element. So in that case, name first element. Like so. Then, for the second element, you can use the prefixes. So you're just going to do the same as this, but you can use prefixes. Now these prefixes would be mono, di, tri, tetra. I think you've heard of it before. I think a good example is carbon dioxide. Now, carbon and oxygen are both simple nonmetals, or if I'm not mistaken. But when you combine them, they use the prefix. They use the prefix di as an example. So that's how it works. You use prefixes for those compounds specifically. Sometimes you can use the prefixes as well for the first element. So in that case, we have diphosphorus pentoxide, which is written as P2O5. So it depends on the situation. Lastly, we have metallic bonding. So these are formed between multiple metals. So these metal ions line up in a repeating pattern, and the loose electrons act as a glue. So they're kind of swarm. There's like a bunch of them, right? Like right beside each other. They look like grapes. That's how their drawing is. And they're all positive, by the way. So the electrons are just making them stick together for whatever reason. Okay, so that covers all the chemical bonding. Okay, I expected to be done with this a bit sooner. My apologies for taking much longer than I thought. So that just implies there will be another one. I'll just first conduct my thoughts on live streaming, specifically on this platform, and then when I'm done, I'll decide if I should record, which I think I should, or if I should continue with live streaming. Okay, let's move on to our next topic. I might have to cut it midway just in case I need to sleep. But as we move on to our second lesson, let's have a quick word from our sponsor. Now, I am sure most of you are familiar with this product. And I assume most of you probably even purchased this product. And even if you have purchased it, unfortunately, nothing's stopping me from talking about this product again. This is a product from Bandy Bears. They simply infused these strap bands into a stuffy and made it perfectly clingable into your arm or anything that could fit its very huggable arms. Now, as you can see, it is a very squishy toy. And obviously, it's very cute. I mean, who can look at this guy and say that this isn't cute? So, I recommend you go buy some. This helps with stress, and I mean, it's just pretty cool. Imagine walking around in public with this. People are definitely going to look at you weirdly, but to me, that's fine. So, they come with many designs. Maybe you don't want a capybara. Maybe you want Stitch. Maybe you want pink capybara. Maybe you want Tung 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 Sahur. Because, believe it or not, they have that. Feel free to pre-order at any time. Their pre-orders are still open. Feel free to contact them on their IG. That is Bandy Bears Official. Bandy Bears Official. So, feel free to message them if you want a specific pre-order. And that is all for now. Okay, back to the video. Man, it feels cool being actually able to do that. It feels so cool being able to actually advertise. Okay, let's move on to our next topic. Now, our next topic here is the building blocks of matter, which I'm pretty sure you guys know are atoms. Now, I'll speed over this again because I talked about this a little bit in another video. So, atoms have protons and electrons and neutrons. So, if I were to draw an atom right here, so you'll have a center, and then you're gonna have these ring things that go around it, like so. Alright, that's your atom. So inside the nucleus, you have the proton, which is the positive charged particle. You also have the neutron, which, just from the word neutral, has no charge. And then on the outside, on these orbits, you have the electron, which is negatively charged. Now, when it comes to their value, because believe it or not, these particles have values. As you can tell with the ionic compounds and the ionic bonds, you saw that some of them had +2, you saw some of them had -2. So in this case, how do we get those values? Well, it's pretty simple. There are rules that we can apply so that we don't have to open up an atom and manually count, because that's impossible. So we're going to use these rules. So we know, for some reason, that the atomic number of any element, the atomic number is represented by Z. I think it has a little thing in the middle. This is your atomic number. Now the atomic number is equal to your protons. So if the atomic number of an element is 12, that is how much protons it has. Now, fun fact, or rather, quick question. What is the element with 12 as its atomic number? I don't know, but I can tell you what. It has 12 protons. So, that's how you get the configuration or the value of the proton without having to count it. Next up is electrons. What if I told you you can also do the exact same thing? Now, again, it is quite similar. The atomic number is also equal to how many electrons there are. So this can equal to the electrons, and it can also equal to the protons. So again, if I were to tell you that chlorine, which is the 17th element in the periodic table of elements, it not only has 17 protons, but it also has 17 electrons. So again, the atomic number represents the electrons and the protons. Or does it? Well, according to this, it doesn't. According to this, it does. So, excuse me. Sorry. Now for the atomic mass is the total number of protons and neutrons in an atom's nucleus. So keep that in mind. The mass is equal to the amount of protons and neutrons within its nucleus. Sorry. So the atomic mass, I'll write it here on the side. Atomic mass is equal to the protons plus the neutrons. I'll just label it as N. And the neutrons. So that's how you get the atomic mass. That's why they have like very weird numbers. Because apparently you can have 0.8 of a particle. Okay, so now that we know how to get these simple values of the electron, the proton, and the mass and the neutron, let's talk about some quick rules. Firstly, being the octet rule. I don't think I'll be able to write all of this down, so if ever, I'll just upload it online. Sarah Nell sent the presentations, the PowerPoint. So if you learn better by just reading the PowerPoint, by all means, go to the PowerPoint. I don't know what you're doing here watching this video. So it's the octet rule. It states that an atom will be most stable when surrounded by 8 electrons in the valence shell. Now an atom does not have 8 electrons. An atom that does not have 8 electrons will bond with another atom to have 8 electrons. Again, that is why ionic bonds exist. One metal, simple metal or non-metal, wants to combine with another one to make sure that it can be stable. But how do you achieve stability? Well, I'll tell you what. You achieve it by having 8 electrons, which is what you call those elements as noble gases. There you go. They're called noble gases. So that's why they do those things. Now, another important thing to note is that all metal elements from groups 1A to 3A need to lose electrons to become stable. So these ones don't receive, they give. So all metal elements from group 1A to 3A need to lose electrons to become stable. The number of electrons lost by metal elements will become their charge. So that is actually a very quick topic. Now, rather than continuing on with the next topic and having to end on a cliffhanger, I will end here. Now, I will admit, live streaming here is a bit more scuffed because the camera angle is a little weird, and probably because I'm not feeling too great, I can't really teach in a very coherent manner. I hope that at least you still learned something. Maybe a little refresher, perhaps. Because this is all I'm doing is just refreshing. I'm actually kind of surprised that this is going to be included in our exam. Because I thought we were over with this, but we're not. So, consider this as part 1. Part 2 can release tomorrow. I will see if I'll live stream it or not. So, in that case, that has been science or general chemistry of the antimatter. And I will see you in the next one. Bye. Oof. Okay, I'm still here. Because I don't know how to end this thing properly. But bye.